All right.
It is.
It could be actually. I don't know. I don't know what this thing is. It's been here for a couple weeks now.
I think it's a robot.
I don't know. It's got an email address.
What kind of robot?
Oh, that might be a printer. But that's still technically a robot.
I saw the rollers on the bottom. I thought it was a printer at first.
I'm not sure what it is. All right. So anyway, for the folks who are watching the video, we've been sitting around talking about weather because those storms are coming through right now, and we've been looking at satellite pictures and stuff like that because I'm a total weather nerd, and I could have gone on about that for like the rest of the semester. So we should not. All right, so we're going to continue. Now today we're not going to do any grading. We haven't actually done any grading in a couple days, but we're not doing any today because I suspect this would not be a great day to do that. Okay? My suspicion based on what I saw on Monday in Trig and an hour or two ago in Trig is that maybe not everybody's as ready to be showing me stuff as they should be. Okay, so you can we'll kind of make Thursday be a day where we're doing more of that kind of grading and stuff like that. Make sure I suspect you guys have a lot of it done. It's more a matter of like, is it organized? Do you have it with you, etc.
Right.
I don't even believe that Jared has it done. It's just something.
Actually, remember I did get my last assignment done in class. So.
I'm always impressed. All right, so we're going to just move forward here. This section 4.5 that we're in the textbook right now is kind of putting some things together. What's better, Jared?
Nothing.
Okay.
Keep going.
Anyway, putting some things together kind of all in one place that we've seen pieces of already, and we're just going to be, using the properties of like first derivatives and second derivatives to help us know a thing or two about graphs. Are you missing a phone?
Yes.
Where do you think it is?
I don't know.
I don't know what to tell you, buddy.
Yeah.
All right. So here's the deal. Let's think about the idea of this section is that we're going to be able to use things like the first derivative and higher order derivatives, particularly the second derivative, to tell us things about what graphs of equations should look like. Like where are the maxima, where are the minima, and other critical points. And also, if we know that there's a critical point there, is it a maximum or is it a minimum? And like the curvature or the concavity of the graph. So we'll talk about that in just a second here. But let's get back here because it's been a while since we've been thinking about derivatives. Jared, when's the last time you thought about derivatives?
Probably last class.
Probably the last time we met, right? I get it. That's the last time I thought about this stuff too. All right. Well, let's talk about it here. I've got some graph here, and here's a function. Okay, we've got some graph of this function here.
Actually, I saw a graph, and I did think because it had the little swirly thing.
Oh,
neat. I thought it was great.
You saw a graph. I'm excited about that.
Yeah. I think. Where was I? I think I was at my dad's work out at Vector, and they had a big windy graph, and I was like, cool, derivative.
All right. Well, here's our graph. Now, remember, the whole idea of this business of derivatives is that they tell us at any given value of x what the slope of the tangent line would be. So, like, if this is our function f of x, okay, if we wanted to know something about what is the slope of this function at some value of x, we get that slope of that tangent line right there, which I didn't draw great, but you know what I mean. That slope of this here is f prime of x. We take the derivative of f, and that gives us the slope. If the slope is positive, it's sloping, the function is running uphill, as you go to the right. If it's negative, it's going down. And we've used this tool actually before to find maxima and minima because the places where the slope is 0, like f prime of x at this value of x is 0, so it is a maximum or a minimum. We don't yet know which. Well, a tool we've actually already used before. And the book kind of gets all, let's be real super technical about all of this here. Okay, so section 4.5 is derivatives in the shape of the graph, and it talks about the fact that, actually, if you just found f prime of x, any range of values of x where f prime of x is positive, means the function is increasing. So like if we actually computed the derivative of this function all the way from way out here to right here, the derivative would be positive. Because all through this range, the function's it's increasing. Are you raising your hand for the question?
Yes, I do.
Oh, okay. I wasn't sure if you were stretching. I had a question.
No.
I'm excited. Jared has a question.
Yeah. So in a way, like you know how sound waves.
Yes.
You use derivatives to find like the peak of the sound wave and the.
Absolutely, you could. Any kind of wave type thing. Absolutely. You're trying to get me back on the subject of weather. No. Similarly, I'm going to use this colored pen here. Any range of values where f prime is less than 0 would mean that the function is decreasing. So like if I had this same function here, from here through, I guess about here, we would know that in this range of values of x, f prime of x must be negative. Because through all this region here, the derivatives, the slope of the tangent line is negative. The function is decreasing. This is part of what your book is calling the first derivative test. And the book gets all a little bogged down about, oh my goodness. At the top of page 391, it would take forever to like parse those sentences. It is being super technical about what if there's like, the derivative doesn't exist at this point? What if the function doesn't exist at this point? What if there's a discontinuity? All that kind of stuff. But then when we actually do the problem sets, there aren't really that kind of problems coming up with it. But this idea that we should be able to draw a graph, and from that, just from that graph, be able to come up with ranges over which we can think about what the derivative sign, if nothing else, would be, is a good thing. So like, in your book, they've got some function that looks something like this, and they talk about the fact that this, just the graph alone, would be telling us that like from here through this way, the derivative with respect to x is positive because the function is increasing, and then through about here, the derivative would be negative because the function is decreasing, and through here it would be positive, and so on. And you know, whether for good or for bad, you're going to have some of these on the homework set, where you're finding like these ranges where the derivative is positive and when the derivative is negative, as well as, of course, where the derivative is 0. Now, on these, most of the time we could think, well, if the derivative is 0, this is a local maximum or a local minimum. But what about ones where, like, it does something like this? You know, where there is a place along the way where the derivative was 0, but it isn't a maximum or a minimum. What's going on back here?
He's wondering if you could find the peak of a mountain using derivative.
If you had the equation to describe the shape of the mountain, sure.
I just didn't know if you could, like, if you were standing at one spot
Mm-hmm.
and you found and you used derivatives of like
Uh-huh.
an angle, if you could
Yes.
find the peak.
Yes, you sure could. How very cool. Again, I could tell you meteorology stories, but we won't do that. I'm impressed he's got in for Student of the Year.
Could you find the slope of how the clouds move around the mountain?
Oh, you
Depending on,
bet.
weather pressures and
Oh my goodness.
temperature change?
Don't try to get me started on weather. All right.
I think we should involve that today.
No,
Just one map.
we'll see more. All right. So let's say we had some function. I'm going to just write some function down. I'm not going to draw its equation, its graph, or at least not yet. But let's write one down. How about f of x equals the sine of x, how about 1 plus the sine of x? Okay, that's such a big deal of a function. All right. Let's find places where the slope of this function is 0, that is to say the derivative is equal to 0, because those are at least candidates for being like maxima and minima. So let's take its derivative. Derivative of 1 is 0. Derivative of the sine of x is cosine of x. So any place where this derivative can be set to 0 is a place where the slope of the tangent line is 0. That could be a maximum or a minimum. So if the cosine of x equals 0, well, you might have to use a unit circle, you might have to use your calculator or something like that. But this is actually true at a large number of points. It's going to be true at x equals pi over 2, 3 pi over 2, 5 pi over 2, and so on. So we know this thing has some places where the slope is equal to 0 because we can take its first derivative and we can set it equal to 0. And how do we know though? Alright, so I know, if I make my number line here, that there's places like x equals pi over 2 and 3 pi over 2 and 5 pi over 2, and for what it's worth, the negatives of those as well. How do we know which of these are maxima and which ones are minima, though?
Well, it'd be every other one, right?
Well, okay, this particular case is its sine. Yeah, I understand. But we can use our big calculus brains to figure out how we're going to know which ones are maxima and which ones are minima. Let's think about what a maximum looks like. It's a place where the slopes were positive, they became 0, and they got smaller, and they became negative. In other words, the slopes were changing. We need to figure out the change in slopes. Hey, that's a second derivative. The second derivative is how the slope is changing. Notice how the slope is going from being a positive number to being 0 to being a negative number. The slope here is decreasing. In other words, we need the derivative of x to be decreasing. In other words, we need the second derivative of x to be negative. So if we're at a place that is either a maximum or a minimum, we know because the slope is 0. Now let's find the second derivative there. If the second derivative is negative, we're at a maximum. What about if we're at a minimum? We're at a minimum, we go from negative slopes to 0 slopes to positive slopes. Slopes are increasing. Slopes f prime of x is increasing. So the second derivative is positive when you're at a minimum. Alright, so apparently we need the second derivative of this bad boy. Second derivative. Second derivative of x will be the derivative of cosine. What's the derivative of cosine?
Negative sine.
Negative the sine. Okay, so we know each of these places where the slope was equal to 0. Now, let's plug some of these guys in. So like if pi over 2 is one of our values, we know that the slope of the function is 0 here. So it's either a maximum or a minimum. Well, it's a candidate for being either a maximum or a minimum. It could be like an inflection point or something like that. Then the sine, what's the sine of pi over 2? You have to use your unit circle or your calculator. Pi over 2 is this one over here. The sine of pi over 2 is 1. It's negative the sine of x. So that is a negative number. It's a negative number, so that is a maximum. So at pi over 2, we hit a maximum. At 3 pi over 2, 3 pi over 2 is this one right here. The sine of that is negative 1, but there's a negative in front of it. The whole thing is positive. The second derivative is positive, so we're at a minimum. And we keep going like this. So we're like this. And drop it We figured out whether they were maxima or minima by whether or not by the sign of the second derivative. A second derivative that's positive is going to have be at a minimum, a local minimum, and a second derivative that's negative is going to have be at a maximum. We have a better word for this. We could talk about the shape of this rather than being maximum or minimum. We could talk about the concavity. Concave, which way it bends. Maxima are at concave down, whereas maxima are at concave up. They're facing, the letter C would be facing upward, like it's catching water. Here's the deal. The maximum itself isn't the only place that's concave down. In fact, any place, like right through here, I mean, the curvature is this way, here the curvature is this way, here the curvature is this way. You can have the concavity of the function, it doesn't have to be at the maximum. It's just the opposite, that at the maximum, the concavity has to be positive, has to be down. In other words, you have to have negative second derivative. But actually, all through these places, if we were just told to sketch the function, we'd want to make sure it bent this way, because its second derivative is negative. Similarly, yes, at the minimum, it's concave up, and the second derivative is positive. But I mean, actually, all through these places here, we're concave up. We're facing upward. It isn't until we get to this inflection point that we'd be changing this from positive to negative values of the second derivative. Where do you think Jared left his phone?
That's none of my business.
Well, I mean, should we anticipate Jared being back? Is where I'm going with this.
He has to be back.
Yeah, that's true. He left his stuff. All right. I'm having flashbacks to our bad experience a few weeks ago at school where somebody left to get their stuff and there was a car accident and all that stuff. Anyway. All right. So, this business of applying the second derivative is what your textbook is calling the second derivative test. Again, they're making way more out of this than it needs to be for the... In fact, I wish I'd left the projector on. I don't want to reheat warm the projector back up over just a little thing. But like, your book in this section, 4.5, is full of like tables that say, you know, like, first derivative is 0, second derivative is positive, therefore it's concave down and it's a minimum, and things like that. Okay, well, you can kind of reason it through more easily than you can remember those tables. In some ways, the book is making more of a hill of it, than it is. All right, so there's really not that... It's kind of just combining some things that we do. I like the fact, though, that this section fell right after spring break. Because here's the deal. In the homework assignment, there's a bunch of taking derivatives. Right? I mean, clearly what they're going to have you do is they're going to give you a function. F of x equals e to the x times the sine of x. And they're going to say, find the first derivative, the second derivative, sketch the function, and find its maximum and minima, or something like that. Okay? Well, what do you have to do?
E to the x is e to the x.
You gotta do this. What rule is this? This is a product rule problem, right? Because we got two things here. So, like, for example, and let's do this one. F prime of x then is derivative of the first, which, as Matt wisely pointed out, derivative of e to the x is e to the x, times the second, plus the first, times the derivative of the second. Derivative of the sine is cosine.
Right.
All right? So you gotta do those things first, right?
And then
I like the fact that there's not really a horrifying amount of new material in this section, so much as in, what do you think they're going to make you really do? Power rule, chain rule, product rule, function rule. Did you find your phone?
No, I went to the bathroom.
Oh,
why didn't you look for your phone?
Because I'm not walking outside in my truck.
Oh, it might be,
Oh, it's
okay.
in your truck.
I wasn't sure if you had it a few minutes ago or something.
I thought I had it in here. It might be up in the comments. I don't know. It's not actually my phone. But so if I lose it, I'm not even worried.
Whenever you find the derivative of e to the x of sine, and then you find the next derivative, and then the second derivative,
Yep.
it looks like it gets more and more complicated, but does it become more and more of a straighter line?
What?
Because whenever you find whenever you find x squared, find the derivative, it becomes more and more of a straight line. The more
Polynomials,
derivatives.
you're right. Anything that's a polynomial. Remember, like if you had f of x equals 3x squared plus x plus 1. You're right. The first derivative of this will then be
Kirby.
6x plus 1.
Just say curtain.
The second derivative of this will just be 6, the constant, and the third derivative of this will be just 0, right?
So it gets,
It gets to be, yeah, but the sines don't work that way, right? Because when you have sines and cosines, the derivative of them, it never becomes, right, derivative of sine is cosine, derivative of cosine is negative sine, derivative of negative cosine will be negative cosine, derivative of negative cosine will be sine. It just repeats.
it infinitely gets more.
Ah,
and more
yes,
Kirby.
well, because they are transcendental functions, but you remember that from trig.
No.
No one remembers that from trig, that's the problem.
That reminds me of there's this one map theory or whatever that if you draw lines around a coastline
Yep,
on an island.
yep.
and
There's
you'll-
no distance around.
Yeah, you can't figure out the
Yep.
true distance because then you can use smaller
Yep.
increments of measurement.
Very
and
good
larger
point.
and larger.
Yep.
And
The
it
closer you look, the more wiggles you gotta go, right?
So technically it's infinite.
Is it, or is there a limit? I can't remember how it works.
I think they said I'm pretty sure they said infinite because
Yeah.
you can continuously
Certainly.
grow and you can't.
Yeah.
There's not something that you
That's because that shape is a fractal. Did you remember that term? Anyway.
fractal.
Anyway, yes, hold on just a second. Okay. Where am I at here? Ah, stop doing that.
Literally.
Conspiracy theories are true.
Alright, so for today,
Okay.
page 403, it's numbers 201 through 215 odd, and 221 through 239 odd. And it's a fair amount of sketching. I would recommend, for any of them that are at all complicated and or any of them you want to check your work on, you know, Desmos.com or whatever your favorite thing to use on your calculator, your phone, or WolframAlpha.com or whatever would be great tools for that. Okay, I don't know that I would be trying to do it just like from scratch out of, you know, fully formed out of your brain. Okay? Because some of them, if you take a look at the problems, get a little complicated. I mean, a lot of them are going to be, because what are they really going to do? They're going to be reviewing all these, like, you know, quotient rules and stuff like that. So, you know, your f of x is going to be something horrible like sine of x over the cosine of x plus e to the x. You're like, well, I don't have the slightest damn idea what that thing looks like. Okay, you're going to want to use some kind of graphing tool to at least get you that shape, right?
Okay.
So that you can be sketching it and so on, and then you could be finding, oh look, it's increasing, you know, the questions will be asking these like, over what ranges is it increasing and decreasing? Or what are the maxima or minima and so on. Okay, you don't want to be doing this all from, you know, reinventing the wheel and like plugging values into your calculator hoping to figure out the shape of the thing. Okay, use tools. Make sense?
Since May.
Sense made. Okay. All right. All right, well then I'm going to turn this thing off and upload it for the other guys. All right.